Alright, hello everyone. Welcome back to another video in my series of going over blind 75 problems on LeetCode. Today we will be going over a new data structure called the binary tree. This problem pertains to that. It's called problem number 104, maximum depth of a binary tree. So before we read this problem, let's first learn about what a tree is. So a tree is kind of like a list, but it's displayed differently. So we have each of these circles here, which are referred to as nodes, with an data element inside of it. It reads from top to bottom, and the topmost node, or the first node up here at the top, is known as the root, where the tree starts. There should be no incoming, or there shouldn't be any incoming node from this first root. So that's how we know that this is the root. And then with a binary tree, each node has 2 children or less at most, so maximum 2. You can see right here. Yeah, everything has 2 or just 1, like these, or none. That's also fine. It just can't have more than 2. So that's a binary tree. And so we have some different terms right here. This one is depth. So let's go and read this problem. Given the root of a binary tree, return its maximum depth. So a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. And I forgot to explain, but so if a node has 2 nodes coming off of it, then or any node coming off of it, then that node is referred to as a parent. So 2 is the parent of 4 and 5. Likewise, 1, which is the root node, is the parent of 1 and 3, or 2 and 3, sorry. And then if you have a node that doesn't have any nodes coming off of it, like all these bottom ones, these are referred to as leaf nodes with no children. So we have parent and then we have children. So right here, this says binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So the root node right here is 3, all the way down to the farthest leaf node, which is either 15 or 7 in this case. And so we do count the root level. So this would be 1, 2, 3. So our output would be 3. Now if we were given 1, null, 2, then that would mean we have 1, and this is null, and then this is 2. So this one would give us 2 right here. So we have this level, and then we have this level. Okay, so given the root of binary tree, we're returning its maximum depth, and in the input we have given tree node values, and in the output we have to return its maximum height. So let me go ahead and actually give you another example here. Let me just draw a sample tree right here. Okay, so we would refer to this, this, and this. These are levels. So 1, 2, 3. So this would give us a height of 3, because this is the root node, which we count as a level, and then we keep going down until we hit the farthest leaf node, which in this case is any of these. These are all same distance. So this would be the 3rd level. They're all on the same level, so we give this a height of 3. Now, by using recursion, tree problems are actually, very widely used with recursion, or solved with recursion. So we know the root and its child. So we go deep inside to its left, theoretically, and then to its right. And from there we can get the deepest root to child value of its left and right. We can compare both of them, and that will be our kind of like induction, sort of, in which one has the greatest value will be added to 1, as well as the root count. Now in this, the smallest valid input could be the root if the root is null. And that would be like our base condition for our recursion. So let's understand this. Try to understand this. Let me get rid of this, this. Actually, let me just draw another tree. Okay, so this is right equal to 2 if we go down the right path. And if we go down this left path from the root, then left equals 3. Because this is 1, 2, so that gives us a height, that we went down 2 levels, so this would give us a height of 3, whereas this would give us 1, 2, 3. Go all the way down to the farthest leaf node, and that gives us 3, but we're counting the root as well, so that would give us 4. So max height we get is 3, but we have to add the root as well, so it will be 3 plus 1, which is 4. Okay, so with all that out of the way, let's finally go ahead and start coding this. Let's see here. Yeah, we won't even actually need a helper method. We can just write our recursive solution here. So first, let's do our base condition. If the root is equal to null, we can just return 0. Now here, let's do a call left, and we're going to recursively call the max depth function or method with root.left. So this is recursively going to go down the left side until we hit null. So right here, this would go down root.left, which is its left child, and then we would keep going down the leftmost path until we hit a null. And then int right is equal to max depth. And similarly, this does the same thing, but going to the right. And now we can just return the max of left and right. And then we want to add 1 onto it to account for the root. So you can see here we'll go through this entire left child right here of the root. So we'll eventually have gone through all this, and it will keep track of the highest number and store that in the left, and then similarly with the right. Right, and so that's all it is for this solution. It's pretty short, so let's go and submit it. And there you go. 0 milliseconds. So the time complexity of this is order of n, and that would be because we are recursively going through, n number of nodes right here for the left and right. And then the space complexity is also order of n. Since we're dealing with a tree of n nodes, so we're actually recursively calling max depth n number of times technically. So okay, and let me go ahead and do a C++ demonstration as well. So this is giving us a pointer to the root, so similarly, it's pretty much similar, pretty much the exact same code almost. There you go. So it's pretty much the exact same solution. Okay, so now let me go ahead and show you guys the Python solution, which is a bit different, or it goes about it a bit differently. So on Python solution, we're going to be using a depth-first search. And what's a depth-first search? Well, it's a kind of algorithm for traversing, trees and graphs and such. So the depth-first search, uh, we start at the root node, and then explore as far along as possible along each branch before we backtrack. As you can see right here, so the basic idea is to start from the root and then mark the node and move to the adjacent unmarked nodes and continue this loop until we have no more nodes to travel to. Then backtrack and check for any other untraveled nodes and traverse to them. And then finally print all the nodes that we reach along the path. So let's go over here. Let me just wait for this to finish. Okay, so we start at 1, travel to 2, travel to 0, go back to 2, go to 3. There you go. So start at the root and then we travel as far as we can through every node in this path for 1. So you can see 1, 0, and then we are now back to 1 and 2. So we can now backtrack back to 2, and then we can go to 3, which doesn't have anything to it. So, and now we have traveled through every node. Similarly right here. So these are graphs, so we can just select any node. But if this is a tree, then you would always start at the root. So 2, let's go ahead and start with 0. Then we go to 1, and then we go to 3. And at that point, we can't go anywhere else from 3, and so we would backtrack to 1. Everything is explored already, so we backtrack to 0. Everything's already done, and then back to 2. So that's kind of what we want to do here with this Python solution. Okay, so let's go ahead and create variables x and y, which I want to initialize both to 1. And if tree.left and tree.left are equal to none, x is equal to self.dfs. Tree dot oh, sorry. This should be max depth. And this should actually be root. Root.left. If root.right and root.right not equal none, we can just return 1 if those are both none. Which this would mean that we would only have the root and nothing else. Return the max of x and y plus 1. Sorry, actually I meant to put this in a helper method. This should actually all be in a function called DFS with a self and tree. So I did have it right before. I just got confused by the method headers. Sorry about that. Let me just change all these again. Root should be tree right here. Self.dfs. Okay, sorry about that. Okay, and now in this max depth, I want to do if root, and we'll say answer is equal to self.dfs with the root, else answer is equal to 0. Then we can just return the answer. Okay, let me see if this works. Yep, there you go. So you can see we're using DFS to traverse the path and then returning the depth to its parent. At each node, we're getting the depth of its left and right subtrees, and then we're returning the bigger of those, +1, to account for the root. And this is also same time complexity, order of n for time and order of n for space. Okay, so there's actually another type of traversal we can do right here for our Python solution. It's called pre-order traversal. And there's 3 different types, but I'll just go over the pre-order for now. Where is it? This is in order, I think. Okay, so a pre-order traversal is so basically traversals are, the order in which we visit nodes. And we have pre-order, in-order, and post-order. So for pre-order traversal, we first visit the root, and then we traverse its left subtree, calling pre-order on left.subtree, and then we've traversed the right subtree. So right here we would explore the root and then explore this entire left subtree before we touch this right subtree. That's post order. Okay. So let me go ahead and just get rid of all this. We're going to do this iteratively instead of recursively. Just to show you guys that you can do it both ways. Or you can get solutions with using recursive and iterative. So let's see here. I guess I can also explain the other types of traversals, even though we're not using them in this problem. So in order is where we, right here, we traverse the left subtree, then the root, and then the right subtree. So this left subtree, then the root, and then the right subtree. And then post order, the left, right, and then root. So left, right, and then root. You can see how each of these are different. We'll be using the pre-order though, starting with the root and then going left and then going right. So if not, why is that red? Let's see here. Okay, if not root, we can return 0. Let's go and create a stack, sort of. I want to store root 1 in here, a tuple, res equals 0. So while stack node and depth is equal to stack.pop. Res is equal to max res of and depth. Oops, spelled this wrong. So right here we're doing the traversal. Node.left, stack.append, node.left, depth +1. If node.right, stack.append, node.right, depth +1. And then we're just going to return res. So this is our way of keeping track of the nodes that we come into. Because when we go back up through the traversal, we're going to want to pop, but while we're going through the nodes, we want to append them. So let's go ahead and submit this. And there you go, that also works. So there's a lot of different ways you can do this. There's a lot of different tree terminology and algorithms that exist, especially for traversions, but these are kind of the ones that are easy to do. But I think that does it for this video. So we've gone over many solutions, and that was the maximum depth of a binary tree, so we got to go over another type of data structure today. So thank you all for watching, and have a great day. Bye.